Good afternoon, everyone. It's amazing to see so many people come out to see some live science, so thank you for a start for everyone coming out today. It's amazing. Welcome to the Embassy Theatre. My name's Ian Hall. I'm an astrophysics writer for The Average Scientist, and I'm here today to talk to you about planet Earth. A quick word before we get going on The Average Scientist. We are a STEM resource website featuring science articles and education written in an accessible format so anyone can understand them. As well as writing articles, we also produce a variety of other content, such as videos, a podcast, and we also conduct live science presentations and lectures, such as this one, which we call TAS Talks. If you're here representing a school today, and you're interested in hosting a TAS Talk in your school, or if you're from a venue and you're interested in hosting a TAS Talk in your venue, please come and see me after the presentation, and I'll be happy to give you some further information. Okay, so the first thing that I want to talk to you about today is something called the overview effect. So if anybody's got one of the excellent In Orbit programs that are available from the theatre, you might have read about this already. But if not, I'm going to tell you about it. So Jerram created this amazing Gaia artwork with the overview effect in mind. And it's something that was first reported by NASA astronauts when viewing the Earth from the Moon. Against the blackness of space, astronauts reported that our home planet seemed small and fragile. Some felt an overwhelming sense of responsibility to protect it, whilst others felt that petty disagreements between people, or even wars between nations, seemed somehow insignificant. The overview effect is created in us by seeing our planet in a way that we've never seen it before. So if you've experienced any of these types of feelings when seeing Gaia for the first time today, you're in extremely good company. Let's have a brief look at what we're going to be going through in today's TAS Talk. I'm going to conclude this foreword in a moment by showing you one of the most profound pictures in 500 years of science. And we'll take a moment to listen to some words about that picture as well. After that, we'll get to the part that perhaps some of you are sat here for today, and that's some planetary science. We'll look how, when and where our planet Earth was formed and why it's spherical. We'll also take a detailed look at one of the most influential forces in the universe and some of the weird stuff that it makes. Finally, I'm going to hand off to my colleague Dane Pavitt. Dane is a content creator and writer for The Average Scientist, as well as a climate change campaigner and a prolific YouTuber with 250,000 followers. Dane is going to be sharing some important information with you about some of the things that we can do to protect planet Earth, and more importantly, some of the things that we simply must do. Okay, so let's get going and have a look at this picture that I was talking about a moment ago. There it is, it looks kind of black. Has anybody seen this picture before? Does anybody know what we're looking at? Nobody? Okay, so the picture is called the pale blue dot. And as we've all had an opportunity today to see planet Earth very close up, I wanted to show you this picture because this is actually a picture of planet Earth from a very, very long way away. And if you can't quite pick out the Earth in the picture, it's there in a red circle. Now, when this image was processed, NASA immediately understood its significance. It's a scientific picture, yes, but it's more than just a picture of our home planet from a long way away. The picture itself was taken by the Voyager 1 space probe on Valentine's Day 1990 at a distance of around 3.7 billion miles, or around about 40 astronomical units, if you're familiar with that type of scaling. Now, NASA needed somebody to make comment on this picture to provide some narrative to accompany it. They needed a scientist, of course, but also someone with a powerful command of language, someone who could convey the significance of the picture to people who were seeing it, especially if they were seeing it for the first time, like maybe some of you are today. Now, in my opinion, they definitely made the right choice of person to provide this commentary, and for obvious reasons, he makes a much better job of describing this picture than I do. So I'm going to let him do that for you now.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam.
Does anyone know who was speaking there? Very good, Carl Sagan. And it was, if you enjoyed listening to Carl describe the pale blue dot there, then you should probably check out his 1980 TV series Cosmos, which is available on YouTube. Some of you may have seen it already. And I know that sounds really old, being filmed in the 1980s, but the beauty of some of this stuff is that it doesn't change very much. And in my opinion, at least, Cosmos still represents one of the very best presentations of planetary science ever made. Now, speaking of planetary science, let's explore some ourselves and look how, when, and where planet Earth was made. We begin the story of the Earth 13.8 billion years ago, at the moment of creation, the Big Bang. It's incredibly difficult for us to imagine what our universe was like at this time, and the truth is, as scientists, we simply don't know. There are theories, of course, but nothing definitive. All we can say with any degree of certainty is that our universe was smaller, hotter, and incredibly dense. So dense, in fact, that everything that we see that makes up our universe today was crammed inside a bizarre object, many, many times smaller than a single atom. How long it existed in that state, we don't know. What changed? We don't know that either. But we do know, however, that something must have changed, because in a massive explosion, the universe sprang into life. Now, the initial growth of the universe, which we call the inflation period, happened almost instantly, growing from that tiny subatomic particle-sized object to something like 11 light years across in a fraction of a second. And as you can see from the diagram here, a lot happened in the first 0.01 seconds after the Big Bang explosion. There was nothing, and then in half the blink of an eye, there was everything. I want to draw your attention to this part of the diagram here, where neutral hydrogen forms, because this is another really important picture in science, and we're going to have a closer look at it now. So the image is called the CMB, or the cosmic microwave background, and this is a picture of the very first light that was emitted from the Big Bang explosion into the new universe. It's the fingerprint, or the echo, of the Big Bang. And incredibly, this is an actual photograph that we've taken of it. Now, I don't have time in today's talk to explain to you precisely how we took this picture, but I can tell you what we used to take it and what it means. So what did we use to take the CMB image? Well, we used this, which is called WMAP, or to give it its proper name, the Wilkinson Microwave Anisotropy Probe. Now, the word anisotropy is one that one or two of you may not necessarily have come across before, so let's just take a moment to understand what that word means. It is a property of material, which means that that material is different if we measure it in different directions. And if we go back to the CMB image, we can see that it matches this description perfectly. It's very different in all directions. There's a lot of variation, a lot of different colours. It does look a lot like a weather map. And that is very interesting because what we're actually looking at in the CMB is a map of temperature difference. Now, the temperature differences in the CMB are represented by the colours. The red areas, of which you can see a few areas of red flecked around there, are the warmest areas, and the blue areas are the coolest. Now, the differences in these temperatures in the CMB is tiny. The difference between red and blue, something like 8/100ths of a single degree Celsius. So very, very tiny differences. But it was enough of a difference. And it was enough of a difference for one of the most influential forces in our universe to begin building. Does anybody know what that force might be? Gravity. Very good, sir, yeah. Gravity is the great sculptor of our universe. And as our universe expanded and cooled, and those temperature differences that we see in the CMB began to emerge, it allowed the very first simple elements to be made, hydrogen and helium. And gravity began working with those simple elements, swirling, coalescing, and bringing them together to form the very first stars and galaxies. A lot of time went by, and a lot of stars and galaxies were made. And then 8 billion years after the Big Bang explosion, in a quiet suburb called the Orion Arm, of what we've now come to know as the Milky Way galaxy, a new star was born. Our home star, the Sun. The Sun was formed from a swirling cloud of gas and dust, which gravity began to bring together, making smaller and smaller and more dense, until the atomic nuclei of those simple elements began to bond together in a process that we call nuclear fusion. In an instant, that fusion reaction ignited, and the new star shone brilliantly against the blackness of space. And there was light in our neighbourhood for the very first time. But gravity wasn't finished there, because the creation of the Sun didn't use up all of the matter in that dust and gas cloud. There was a tiny, tiny amount left over. And gravity began again, working with that remaining matter, bringing it together in larger and larger structures which then smashed into one another in a spectacular cosmic shooting gallery that lasted 500 million years. But eventually, there was calm. Gravity had now used up most of that material in the dust and gas cloud, and had brought it together in structures that were large enough and in stable enough orbits to end the violent bombardment. 8 large bodies remained. Some were enormous balls of trapped hydrogen and helium gas that we've come to know as Jupiter and Saturn. Others, massive balls of ice, Neptune, Uranus. And closer to the Sun, the bodies were smaller and rockier and warmer. And in an orbital pattern, approximately 93 million miles from the Sun, was the third rocky planet in the newly created solar system. A planet that the ancient Greeks called Gaia, the mother of life, planet Earth. Now, the creation of the Earth is an amazing story. It's a scientific story, but for us, it has a more profound meaning than that, because it's our story and the story of where we all came from. Another very famous quote from Carl Sagan that we made reference to earlier. He famously said, "We're all made of star stuff." Now, I've spoken a lot over the last few minutes there about gravity. And I want to take a closer look at gravity with you now, because not only is gravity responsible for almost everything that we see in our universe today, it's also the reason why so much of it is spherical. So let's start by having a look at some mountains. Everest, we know, is the highest mountain on planet Earth, but it's not the tallest. There are some mountains taller than Everest. Kilimanjaro in Africa, for example, is taller, and the Hawaiian volcanic mountain, Mauna Kea, is taller again. Now, Everest has its Kilimanjaro has its base altitude slightly lower than Everest, meaning it's taller, but it's not as high. And Mauna Kea, as you can see from this picture, has its base way below sea level, so it's by far the tallest of these three mountains. And the interesting thing about Mauna Kea is that it's sinking. And we're fairly sure that Mauna Kea is about as tall as a mountain can get on planet Earth. Something is preventing Mauna Kea from growing any larger. A force is acting on Mauna Kea to crush it back into the surface of the Earth. And that force is the force of gravity. Now, the place for us to start trying to understand this gravitational effect is here, with potatoes in space. Now, there are no actual potatoes in space, as far as we know, but there are these asteroids. And I think if we think of the word asteroid, or we try to picture an asteroid in our minds, we probably think of something that looks a bit like this. But why are these irregularly shaped? What decides if something is going to be spherical, like a star or a planet, or if it's going to be irregularly shaped, like an asteroid or a potato? Well, the answer is size. If an object is approximately 150 miles across, or 150 miles in radius, or greater, the force of gravity will crush that object into a sphere. Smaller than that, and there isn't enough material for gravity to properly work with, and it will remain irregularly shaped. And in astrophysics, we have a highly scientific name for this scale, and it's called the potato radius. It would appear perhaps that sometimes scientists are so busy doing actual science that when they discover something, they run out of time to give it a scientific name. And we can see how this potato radius works using this sand that I collected last week from Skegness Beach. And don't worry, I will return it after today when we're finished. If I scoop up some of this sand in my hands, you can see that it's irregularly shaped. It's not really a potato shape in this instance, more of a pile. But that's okay, it's irregularly shaped nonetheless. And the force of gravity is acting on this pile of sand right now. It's just not a big enough pile for us to see gravity doing anything meaningful with it. But if we use our imagination, and we imagine that this pile is much larger, greater than 150 miles across, then the force of gravity would begin to crush the material that makes up this sand. And the important thing to understand about gravitational effect is that it works equally from all angles at the same time. So the force is acting on the sand from every direction possible towards the centre of it. And I can simulate that by squishing this sand in my hands, trying to apply equal pressure from all angles at once. And the result is that I'm left with a ball or a sphere. Now, it's the same force that was acting on the young planet Earth 4.5 billion years ago to crush our planet into a spherical shape. And it's the same force that's acting today on Mauna Kea to prevent it from growing any taller. And that is the reason why so many of the stars and planets in the universe, including our own planet Earth, is spherical. It's the force of gravity acting in equal proportions from every angle at the surface of an object larger than 150 miles in radius. We are spherical for no other reason than we simply cannot be any other shape. Gravity makes spheres. Now, whilst the force of gravity acts the same all the way through the universe, the effects of that gravity can be very different in different places. And I want to explore a little bit of that with you now. Question time again. Does anybody know what this constellation is called? Has anybody seen this before? Orion. Yeah, very good. It's the constellation of Orion, and we can see it in our winter skies right now. And I want to concentrate on the constellation of Orion, in particular on the star to the top left, that one. Does anybody know what that star's called? Betelgeuse. Very good. Yeah, it's Betelgeuse. And Betelgeuse is a type of star that we call a red supergiant. And again, another highly scientific name. So let's look at those two words and try to understand them individually. Red. Well, we can certainly see from the picture here that Betelgeuse looks more yellow than the surrounding stars in the constellation and the one on the back. And that would be true. If we were to go out this evening, if we were to look up into the sky, find the constellation of Orion, look to the top left, find Betelgeuse, it would look more red than the stars around it. And the reason for that is because it is red. So that's a nice, easy one to understand. Now, the word supergiant, again, not a very scientific term, but it is one that suggests that Betelgeuse might be very big. But how big? Let's have a look. So Betelgeuse is that big. That's not very helpful in isolation. We're going to need to add something into this diagram for some scale and comparison. So I'm going to ask you another question first. Does anybody know how many planet Earths can fit inside the Sun? Can anybody have a guess at that number? That's a very close guess, 1 million. So the gentleman down here said 1 million, and that's very close. It's actually 1.3 million. So 1.3 million Earths can fit inside the Sun. The Sun is huge. But how big is the Sun in comparison to Betelgeuse? Let's have the Sun into the diagram and look. It's there. And if anybody is struggling to see that from where they are, it's there inside the red circle. So bearing in mind, we can fit 1.3 million planet Earths inside the Sun. It's obvious from this comparison that Betelgeuse is enormous. So enormous, in fact, that we could fit a staggering 600 trillion planet Earths inside it. It is truly a monster of the universe. And gravity in places like Betelgeuse is very different to how we experience it here on planet Earth. Whilst it does the same thing, the effects of that gravity are very different. And when a star like Betelgeuse comes to the end of its life, its nuclear fuel begins to run out. It begins to swell, growing larger and larger and larger, until eventually it becomes so massive that it's unable to support itself, and it loses the fight to the force of gravity. And the force of gravity begins an unstoppable chain reaction on the star, crushing it smaller and smaller and making it more dense and more dense, while simultaneously ejecting matter into the universe in a massive explosion that we call a supernova. But the supernova explosion doesn't blow away all of the material from the star. Something is left behind. And for stars as large as Betelgeuse, their lives are going to end in one of two ways. So what might be left after the Betelgeuse supernova explosion? Well, it might be one of these, a neutron star. Now, as we can see from the picture here, which isn't to scale, but it is accurate enough for us to get a visual representation of it, neutron stars are tiny. They're usually just a few miles across, city-sized stars. And these strange objects have been crushed to become so dense by the force of gravity that if we were able to travel to a neutron star and take just a single teaspoon of material from its surface, it would weigh about the same as the entire planet Earth. Very, very dense objects. But gravity has one more trick up its sleeve. One more trick that is reserved for the death of the very largest stars. And what's left behind after that supernova explosion is the strangest object that we know about in our universe today. Can anyone ever guess what that object might be? No takers on that one. It's a black hole. Very good, yeah. Someone got there in the end. It's a black hole. Now, black holes are an area of space where all of our understanding of science begins to break down very quickly. They've been crushed to become so dense by the force of gravity that not even light can escape from beyond their surface, which is why we see them as black. And a black hole isn't a hole in the way that we might think of a hole like a hole in the ground or a hole in the wall, because gravity sticks to its principles of making spheres. So a black hole is a spherical hole. It's a hole in all directions at the same time. And if we were able to travel to a black hole and cross over its surface, called the event horizon, into the black part, we wouldn't fall through and we wouldn't fall down. We would be crushed, smaller and smaller and smaller, to an infinite point of density that we call singularity in the middle. Maybe it's something a bit like that bizarre subatomic particle size object that existed before the Big Bang. Who knows? Nobody knows. And if you're struggling to picture that in your head, you're struggling to imagine this spherical hole, a hole in all directions at once, and we don't fall through or down, we somehow fall inside, You're struggling to imagine it. I'm struggling to explain it to you. We're all in good company again, because scientists have worked for decades and decades to try and understand these strange objects. And the progress that we've made in understanding black holes has come on a good amount in that time, but there is still so much for us to learn about them and so much that we don't know. Some of the very best work on black hole physics having been conducted right here in this country from our own great Professor Stephen Hawking. So now we've had an opportunity to look at how, when and where our planet Earth was made, and we've learned about some of the strange forces and physics at work. I'm going to hand over to my colleague Dane, who's going to talk to you about some of the things that we can do to protect our precious planet, because it's taken such a long time to be the place that we call our home, and it has survived unthinkable violence in its history, but it might just be facing its biggest challenge in the coming 20 years. Dane.
Thank you. Oh, very much, very kind of you. Right. Thanks Ian, and thanks everybody for coming out. My name's Dane. I'm one of the writers with The Average Scientist. I specialise in biological, earth and environmental sciences. Following on from Ian's chat about the formation of the planet, I want to talk to you about some of the more recent chapters in Earth's history. Ecosystems and the future of Earth by way of climate change. Of course, climate change is a big issue at the moment. There's a lot of debate and discussion going on, but unfortunately there's also a lot of misinformation and misdirection regarding the science, sometimes deliberately so. So what I want to do with the remainder of our time here is try to clarify things for you, explain a bit about how these Earth systems work, the effect that we're having on them, and hopefully inspire you to take some actions of your own. So we'll start with the basics. If you'll obey me, machine, there we go. What is the atmosphere? Well, it's a layer of gas held against the Earth's surface by its gravity, roughly 60 miles thick, depending on where you are in the world, made of lots of different types of gases, mainly nitrogen, oxygen, a little bit of argon, and a small amount of what we know as greenhouse gases, key among them being CO2 or carbon dioxide. Greenhouse gases are very good at absorbing and holding heat from the sun, which is essential for creating a livable planet. Without greenhouse gases, the Earth would be about minus 20 degrees and mostly covered in ice. So naturally, the more carbon there is in the atmosphere, the warmer the planet gets. So over its 4 billion year history, life on Earth has evolved some amazing self-regulating systems that help to maintain healthy conditions. Plants, photosynthesis, famously, plants absorb carbon dioxide out of the atmosphere, they combine it with water and nutrients from the soil, use it to build their cells and release oxygen. A lot of carbon is absorbed into the oceans, where there are corals that use it to build their exoskeletons, there are mollusks that use it to build their shells, and there are huge clouds of algae visible from space, trillions upon trillions of microscopic marine plants, absorbing carbon, releasing oxygen. All of these processes, and a whole bunch of more, turn atmospheric carbon into living organic matter, or biomass. And this biomass forms the foundation of the world's ecosystems. All of these living things, consuming biomass, using that carbon to build and run their bodies, this is an essential part of understanding ecology. Plants, fungi, animals and bacteria are not just decorations within a habitat. They are essential components in maintaining healthy environmental conditions. All of these living things are doing a job without which their habitats would suffer. And when they die, they decompose into the soil, where their biomass becomes fertiliser and food for the next generation. In some very special cases, they are sealed away in the rocks, where they become fossils. And the next stage of this process is for carbon to be released back into the atmosphere, otherwise it would all get absorbed and the planet would go cold. And this happens through erosion, decomposition, respiration, and major events like forest fires and volcanic eruptions. And so the process continues. Carbon is absorbed and released, both processes countering each other, creating what we know as the carbon cycle. Now, for the past 10,000 years or so, this has worked out quite well for us. Average global temperatures haven't risen or fallen by more than a degree or so since the end of the last ice age. And this period of stability has created reliable seasons and weather patterns that we're familiar with, a natural rhythm of hot and cold, wet and dry, that can be predicted and planned for. And this period of stability allowed early humans to make a very important transition from hunter-gatherers to farmers. We no longer needed to chase wild herds or seek out fruiting trees. We could plant, grow, breed, and store the food we wanted in one location, depending on the seasons. This meant that we didn't have to move around as much, so we could build bigger and bigger settlements. We could make cities. This is a reconstruction of Babylon. We could make cities, empires, trade networks. We could pursue architecture, art, music, science, mathematics, philosophy, politics. Civilization as we know it took root, in large part thanks to the enabling forces of those reliable weather systems. Now, while all this was happening on the Earth's surface, something else was going on underneath it. Remember I mentioned fossils earlier. Well, some of those fossils have been held deep within the Earth's crust under extreme pressure and heat, crushed and boiled until they turn into what we now know as oil, coal, and natural gas. Oil is not made of dinosaurs, by the way. I just want to clear that up. It's mostly marine microorganisms. Now, humans learned quite quickly that burning these materials released a lot of energy. And during the mid-1700s, we started doing this on a huge scale, using them to power our machines. This was the start of the Industrial Revolution, an age of massive innovation and expansion, new developments in technology, transport, manufacturing processes. Industry was supercharged, but so was demand. All of that innovation required raw materials, more land space, more and more food, and a constant stream of fossil fuels. This meant that natural landscapes had to be cut down, mined, drained and dredged to meet those demands. A lot of this was done by very rich countries going into very poor countries and taking it all for themselves. And although people didn't know it at the time, all that fossil fuels being burnt was releasing CO2 back into the air. And this has carried on more or less unchanged ever since. So we're releasing excess carbon dioxide into the atmosphere whilst destroying the natural ecosystems that keep those carbon levels under control. And you don't have to be a master mathematician to see where this is going. So remember I showed you that graph of temperature change since the end of the last ice age? Well, this is temperature change within the last 300 years. Now, if all that happens is that the world gets a little bit warmer, it might not be too bad. It might even be pleasant. But it's the knock-on effects of that rising temperature that we need to be concerned about. It's the way that it changes water chemistry, reducing the amount of gas that the ocean can hold. It changes air pressure, which affects our weather systems. It changes the seasonal behaviours and growth of plants and animals. And of course, it causes ice sheets to melt. There's this whole web of interconnected causes and effects and feedback loops, which unfortunately I don't have time to go into in a great amount of detail, but hopefully you can read some of that. At current estimates, we're releasing about 100 times more carbon into the atmosphere per year than all the world's volcanoes. Animal populations in the wild have declined by about 70% in the last century alone, and we're now seeing the impact on people in the rising frequency of disasters like storms, floods, heat waves and wildfires. So, what can we do? I appreciate it all sounds a bit hopeless and horrifying, but unbelievable as it seems, I don't want you to come away from this with dread and despair. I want you to recognise the urgency of the situation and turn that into motivation. There are things we can do, and I've divided them into two categories. There's the little things, which are the things that we can do as individuals, as families, and as communities. And then there are the big things, the large-scale transformative action that we all need to get on board with. So we'll start with the little things. A bathing machine. Thank you. Think carefully about what you're buying. This is a classic. We like to think about recyclables, renewables, and biodegradable materials. Have your food and cosmetics being ethically sourced. Eating less meat or cutting it out entirely puts less demand on livestock farming. But it also applies to non-consumables, your luxury purchases. Take the electronics in smart tech, for example. They rely on minerals like cobalt and lithium, which are extracted from the earth using hugely damaging mining processes and horrific human rights violations. So next time you see an advert on TV or social media for some fancy new gadget like a folding smartphone, a voice-activated home assistant, and I actually can't believe this exists, a fridge with a built-in touchscreen. Ask yourself if that level of luxury is really worth that level of damage. Use your cars less. I am of the somewhat fringe opinion that cars are the worst form of transport. We know they put out a lot of emissions, but they also take up way too much space and require far too many large structures to be built relative to how many people they carry. If you can make a journey by foot, bike, bus, tram or train, please do. It is cheaper, it is cleaner, it is safer, and the fewer cars there are on the road, the better for everyone, including motorists. Creating space for nature. This can be little things like bird feeders, log piles, wildflowers, ponds, but the easiest and most effective one of all is to stop mowing. Whether it's a little urban garden or a massive golf course, lawns are terrible for biodiversity. If you stop mowing for a few months, you'll be amazed at how quickly you get mosses, wildflowers, insects, birds, small mammals. Nature will rush in to use the spaces that we create for it. So now we come to the big things, the large-scale transformative action. Plain and simple, we need to end fossil fuel dependence as quickly as possible and switch to renewable alternative fuel sources. The technology exists, it absolutely has the capacity to meet our needs, we just need to make that commitment. This is a difficult one. We need to find new ways of making food. Right now, farming uses about 40% of the world's land surface, and 90% of the world's seafood stocks are overfished. Some of the most vibrant habitats on Earth have had their biodiversity stripped out to make way for pastures and monocultures. And with climate change threatening our reliable weather systems that farming relies on, this is totally unsustainable. And it goes hand in hand with the next big project, large-scale rewilding. This is something I'm very excited about. Restoring natural ecosystems, giving large areas of land and sea back to nature, reintroducing extinct species, and then stepping away. Give the natural world the space and time it needs to flourish and rebuild the carbon cycle. But for all of these things to have a real impact, small and large, the number one most important thing we need to be doing is demanding better. We have energy companies, tech giants, and food corporations making disgusting amounts of money during a cost of living crisis and at the expense of the natural world. We have tabloid press and major broadcasters giving platforms to science denial and conspiracy theories, and we, as well as a lot of other countries, have a government funded by these activities and whose policies enable and reward them. This is the only planet we have, and if we want to keep it safe and livable, not just for ourselves and for wildlife, but for future generations, we have to come together and take decisive action. We do have the power to make a difference, and I hope you'll all use yours. Thank you very much.
Thanks, Dane. As you can see there, Dane is incredibly passionate about climate change. He does this stuff a lot. He does it in person, he does it online, and I hope that some of the stuff that he's told you today resonates with you, and you will take his advice and take even some of the simple actions that we heard there, even if that is down to creating spaces for nature in our gardens or trying to use our cars less. Thank you very much for your time today, for coming out and listening to a live science presentation. Dane and I will both be down in the auditorium in the next few minutes if you have any questions or you want to discuss any of these subjects with us a little bit more. Thanks very much. Enjoy the rest of your afternoon and have a safe journey home.